Hi friends, welcome to our YouTube channel Knowledge Academy. The main aim of this lecture is to discuss about the IES or ESE technical paper of the electrical engineering solutions from 2017 to 2020. So we are going to discuss in this in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever you upload a new video, the direct notifications comes to mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why do waste more time? So let's get started. Now we are going to solve the first question of this lecture. See the question here. The current in the 1 ohm resistor in the network as shown is. So in the circuit diagram, we need to find what is the current in the 1 ohm. We need to figure out. So only the magnitude value we need to figure out. So what are the four options? Option B, 2.25 ampere is the correct solution of this question. So let's solve this numerical. So this is circuit diagram they are given in the question. So here we need to find what is the current in this 1 ohm. We need to figure out. So if you see carefully, there are only two nodes. This is the bottom node and this is the upper node. So therefore now I am going to assume this as a reference node. So therefore this is zero potential. So therefore the other node voltage will be, so let me assume this is the voltage V. So therefore here if you see carefully, this node has a potential V with respect to this ground potential. So now I am going to solve this question by the nodal analysis. So by nodal analysis we are going to get like this. Means the sum of outgoing currents at a particular node is nothing but 0. Means summation of all the currents which are outgoing at that particular node has to be equal to 0. So therefore here in this branch the outgoing current is V minus 2 by 2. So therefore here plus, and the outgoing current from this branch is nothing but V minus 3 by 2. V minus 3 by 2. And similarly here this has a potential of 0. So therefore V minus 0 by 1. V minus 0 by 1. Here the current is incoming, but we need to find what is the outgoing current from a particular node. So therefore now if it is incoming means outgoing will be minus 2 ampere is equal to 0. So therefore here LCM is equal to 2. So therefore V minus 2 plus V minus 3 plus 2 into V minus 4 is equal to 0. So if you take this 2 to the right side, it will become 0. So therefore this is the thing we are going to get here. So there is only one equation with only one unknown. So if you solve this one, V is equal to 9 by 4. We need to find what is this current in this 1 ohm we need to figure out. So therefore here the current is equal to voltage difference V minus 0 by 1. So therefore I is equal to V minus 0 by 1. It is nothing but V. So V is now equal to 9 by 4. So 9 by 4 is nothing but 2.25. So therefore the current in this 1 ohm resistor is nothing but 2.25 ampere is the correct solution of this question. So now we are going to solve the second question. See the question here. So for the circuit as shown, what is the value of the C that leads to maximum power transfer to the load if the value of the L is 0.5 Henry. So here in this question we need to find C. So what is the value of the C? So therefore the maximum power will be transferred to this load we need to figure out. So what is this particular C value we need to figure out. So what are the four options? Option B, 0.01 farad is the correct solution of this question. So let's solve this numerical. So here this is a figure. So for this figure, this is a source and this is a source resistance, internal resistance, and this is the total load. So for this load we need to find what is the value of C. So therefore the total amount, this maximum power is going to transfer this load. So if you see carefully, the inductor and the capacitor are not going to consume any active power, only they are going to consume reactive power. So therefore we can conclude that only RL, the load RL is going to take the active power, but not the inductor and the capacitor. So therefore now here this is nothing but C. This is nothing but 10 cos 10t is the source voltage, and the internal resistance is nothing but 10 ohm, and the capacitor value we need to find. So therefore the maximum amount of power can be transferred to this load, and RL is equal to 5 and L is equal to 0.5 Henry. So therefore we need to find what is the value of the C in such a way, so therefore the maximum amount of power can be transferred to this load. So here this is nothing but here Vm cos omega t. So omega is equal to 10. So omega is equal to 10. So therefore now this is nothing but, this is inductance value they are given, but inductor reactance is JXL. JXL is nothing but J into omega L. So therefore omega is 10 and L is equal to 0.5. So therefore 5J. So therefore this is the value 5J. This is the inductor reactance of this inductor. So therefore this is 5J. Now this resistor and this RL and L are in series combination, but this C is in parallel combination with this. So therefore here the total impedance of this load is nothing but 5 plus 5J parallel with minus JXC. So therefore 5 plus 5J into minus JXC by 5 plus 5J minus JXC. So therefore if you do the multiplication here, this is the thing we are going to get. So this is the thing we are going to get. So now what I am going to do is I am going to do the rationalization. So therefore 5 minus J into 5 minus XC by 5 minus J into 5 minus XC. And if you do the multiplication, equation here, finally we are going to get, this is the thing we are going to get finally. So now in this there is a real part and also imaginary part. Now I am going to separate the real part and imaginary part. So therefore I am going to separate the real part and imaginary part. This is the thing I am going to get here. So if you see carefully, ZL is equal to real part and also imaginary part, but at maximum power transfer condition, always the ZL will be complex conjugate of the source impedance. Complex conjugate of the source impedance. But if you see carefully, this ZS is nothing but internal impedance. Means internal impedance only, there is only pure resistor. Means 10 plus, there is no complex term, only real part is there, but there is no complex term. So therefore 10 plus J0 whole conjugate. So therefore here you can take here 10 minus J0. So therefore ZL has to be equal to 10 minus J0. But if you see carefully, ZL has real part and also imaginary part. It has to be equal to 10 minus J0. So therefore real part value equal to 10 and the imaginary value part has to be equal to 0. So therefore now I am going to equate this, the imaginary part to the 0, because the real part I am going to equate to 10 and the imaginary part I am going to equate to 0. So therefore now what I am going to do is I am going to equate only the imaginary part is equal to 0. So therefore imaginary part is, this total part is equal to 0 means this value into any 0 is again 0, denominator into 0 is nothing but again 0. So therefore only this upper part now I am going to equate to 0. So therefore now there is only one equation. So therefore now I am going to get in this manner, xc into 50 minus 5xc into 0. See, if x is not equal to 0, compulsory 50 minus 5xc has to be equal to 0. So therefore xc is equal to 10. So x is nothing but 1 by omega c is equal to 10. C is equal to 1 by omega into 10. Omega is nothing but 10. So 1 by 10 into 10 is nothing but 0.01 farad. So if you place a capacitor of 0.01 farad, then the maximum amount of power can be transferred from this source to the load. Only RL is going to consume the active power, but not the inductor and the capacitor. So we have used this fundamental equation, ZL is equal to complex conjugate of the source impedance. At this condition only we are going to get a maximum amount of power can be transferred from the source to load. And if you see carefully, 10 plus J0 whole conjugate means 10 minus J0. So real part I am going to equate to 10. In that manner also you are going to get the value of xc, but it is a very lengthy method. So therefore we are going to equate this imaginary part to 0, then we are going to simply get the solution of this question. See, now we are going to solve the third question. See the question here. For the network shown in the figure, the current flowing through the 5 ohm resistance will be. So in this circuit diagram, we need to find what is the, how much amount of current is going to flow through this 5 ohm resistor. We need to figure out. So what are the four options? Option C, 39 by 28 ampere is the correct solution of this question. So let's solve this numerical. So this is a circuit diagram. For the circuit diagram, we need to find what is the value of the current is flowing through this 5 ohm resistor. We need to figure out. So therefore, let me assume this is the direction current. So direction is not at all important. You see, in the question they have not given any, only magnitude value we need to figure out. So let me assume the direction in this 5 ohm resistor is downward. So if you see carefully, there are only two nodes. So this is ground node. So therefore this I am going to assume it as a reference, means reference node is nothing but zero potential. So therefore there is only another node. So let me assume this is the node. Let me assume this is a phi. So therefore this is a 15 volts. So no need to take this one. So therefore now here this node has a voltage V with respect to the reference node. So by using the nodal analysis, we are going to solve this numerical. So by nodal analysis, the sum of algebraic currents which are flowing out of this particular node is nothing but is equal to 0. So therefore here the outgoing current is in this branch is V minus 15 by 4. This is what I have written, and also the outgoing current in this branch is nothing but V minus 0 by 2. V minus 0 by 2. Here it is incoming current, but we need to find what is the outgoing current. This outgoing current is minus 6. And similarly, the outgoing current in this branch is nothing but V minus 0 by 5 plus 3 is nothing but 8. So therefore V minus 0 by 8 is equal to 0. So if you take the LCM of 4 to 8 is nothing but 8. So therefore here you have to multiply by 2. So 2 into V minus 15. Here you have to multiply by 4. So therefore 4 into V minus 6 into 8, 48 plus V is equal to 0. So 8 take it to the right side. So therefore this has to be equal to 0. So therefore this has to be equal to 0. So only one equation with only one unknown. So therefore V is equal to 78 by 7. So but we need to find what is the, so we have figured out this node voltage with respect to reference node. So we need to find what is this current I. So therefore I is equal to V minus 0 by 5 plus 3, 8. So therefore I is equal to V minus 0 by 8. It is nothing but V by 8. So V value we know, which is 78 by 7 into 8. So therefore here if you 78 by 7 and here into 8. So if you solve this one, we are going to get finally 39 by 28 ampere. So therefore the current in this 5 ohm resistor is nothing but 39 by 28 ampere is the correct solution of this question. So now we are going to solve the fourth question. See the question here. The circuit as shown in the figure is connected to a load ZL across x comma x. So for a maximum power transfer to the load, ZL should be. So in this question there is a load ZL which is connected across this connection x and x. So we need to find what is the value of the ZL. So therefore the maximum amount of power can be transferred to this load ZL. So what are the four options? Option A, which is 3 minus j by 4, is the correct solution of this question. So let's solve this numerical. In this question, this is circuit diagram. So in the circuit diagram, we need to find what is the value of ZL. So therefore the maximum amount of power can be transferred from the source to the load. So what I am going to do is nothing but here, now I am going to find the Thevenin circuit for this one, Thevenin circuit across this. So therefore the Thevenin voltage is, this is the Thevenin voltage. So let me assume this is the VTH. Across the half and minus 3, this total combination, this is the Thevenin voltage, so VTH, and the Thevenin impedance is nothing but it is a, you need to do short circuit, so therefore this is a short circuit. And let me assume this is the total impedance is Z1 and this is the total impedance is Z2. So therefore Z1 parallel Z2, then only we are going to get the Thevenin impedance from this source, from this side. So therefore ZTH. So this is ZTH across the connections, cross. So this is the cross connections. So therefore this is the source. So therefore this is the equivalent circuit. This is Thevenin equivalent circuit across the ZL. So if you see carefully, here they are asking what is the value of the ZL in order to get the maximum power transfer. So therefore the condition is when ZL is equal to ZTH whole cap, means when the load impedance is equal to complex conjugate of the source impedance. Here source impedance is nothing but Thevenin impedance. So if you take this at this condition only, we are going to get the maximum amount of power which can be transfer to this ZL. So therefore here first thing we need to find what is the value of ZH, and then we have to do the complex conjugate, then only we are going to get the particular value of ZL. So therefore the maximum amount of power which can be transferred to this ZL from the source. So therefore here ZTH is nothing but Z1 parallel Z2. So therefore Z1 parallel Z2. Z1 is nothing but 1 parallel J. So therefore 1 into J by 1 plus J. It is nothing but here 1 into J by 1 plus J. It is nothing but J by 1 plus J. Now I am going to do the rationalization into 1 minus J by 1 minus J. So if we solve this one, we are going to get 1 plus J by 2. And similarly Z2 is nothing but half minus J3 by 2. So half minus J3 by 2. So therefore ZH is equal to Z1 parallel Z2. It is nothing but Z1 into Z2 by Z1 plus Z2. So therefore here we know the value of Z1 and we also know the value of Z2. So substitute those values. So therefore Z1 Z2 by Z1 plus Z2. So Z1 is 1 plus J by 2 and Z2 is half minus 3 by 2 J. So substitute here Z1 and Z2. So if you solve the upper part, if you multiply this Z1 Z2, we are going to get 4 minus 2J by 4, and if you add this Z1 plus Z2, we are going to get 1 minus J. So 4 I am going to take it denominator. So therefore 4 minus 2J by 4 into 1 minus J. So now I am going to do the rationalization with 1 plus J by 1 plus J. So therefore finally I am going to get 6 plus 2J by 8. It is nothing but here. Now I am going to take as a 2 as a common. So therefore 2 3s are, 2 1s are, 2 4s are. So therefore 3 plus J by 4. So this is the value of the ZTH, but we need to find what is the value of the ZL. ZL is nothing but complex conjugate of the ZTH. So therefore ZL is equal to complex conjugate of the ZTH. So if you do means plus J, you have to replace by minus J. That's it. 3 minus J by 4. So therefore this is the complex conjugate of the ZTH. So therefore this is called as the, at this value, if suppose if you place a impedance of this value only at this particular condition only, the maximum amount of power which can be transferred to the load, means the total circuit will be a purely resistive at this condition. So therefore the maximum amount of power which can be easily transferred. The answer is 3 minus J by 4 is the correct solution of this question. So we are going to solve the fifth question. See the question here. In the network as shown in the figure, with IS1 is equal to 5 ampere and IS2 is equal to 10 ampere, VAB is equal to 120 volt. And with IS1 is equal to 10 ampere and IS2 is equal to 5 ampere, we are going to get VAB is equal to 15 volt. Then what is the value of K to describe IS1 is equal to K IS2 such that VAB is equal to 0 volt? So therefore we need to figure out. So therefore here out of the four options, option A means K has to be equal to 2.5 in such a manner VAB is equal to 0 volt. So let's solve this numerical. So here this is the circuit diagram which is given in the question. This is a purely resistive network. Here there is a current source with the current direction upward, which is IS1, and there is also other current source in the direction of this one. So therefore IS2. So this is the open circuit voltage across A and B. This is the voltage. So VAB. So here in the question they are given the, suppose if IS1 is equal to 5 ampere and IS2 is equal to 10 ampere, then we are going to get the output voltage VAB is equal to 120 volt. And similarly, if IS1 is equal to 10 ampere and if IS2 is equal to 5 ampere, then the voltage VAB is nothing but 15 volt. And similarly, if IS1 is equal to K times the IS2, so therefore IS2 is again IS2, then the output voltage VAB is equal to 0. So therefore at this particular condition, when IS1 is equal to K times of IS2, then what is, suppose we are going to get VAB is equal to 0, then what is the value of the K we need to figure out. So therefore here, before I solve this numerical, let me tell a small concept here. Say, suppose there is a resistor network like this, R1, R2, here there is a node voltage V1 and here there is a node voltage V2. So now I want to find what is the node voltage VA. So therefore VA is equal to V1 into R2 plus V2 into R1 by R1 plus R2. So now I am going to take this denominator for each and every numerator. So therefore R2 by R1 plus R2 into V1 plus R1 by R1 plus R2 into V2. So therefore this is a constant term. This is a constant term. It is irrespective of the source voltage or source current. It is going to depend only on the network value. So therefore let me assume this is a K1. And also this is also R1 by R1 plus R2. It is independent of the any source voltage or source current. It is going to depend only on the circuit variables. R1 by R1 plus R2 is nothing but K2. So therefore output voltage means this voltage reference, this node voltage is nothing but K1 into V1 plus K2 into V2. It is nothing but here for output, if any output is equal to K times the input 1 and K2 times the input 2. So here the inputs are the currents and the output is a voltage. Now here I have taken only the output is current and input is also, see, output is a voltage and the input is also voltage. But in this case here, the output is a voltage and the inputs are the current. Same concept I am going to apply here also. So therefore the output voltage is equal to some constant times the input. Input is nothing but here source current, and similarly some constant times the input, another input. So the input is current, so IS2. So by using this standard equation we are going to solve. See, these two are in the same manner. Only thing is here I am going to take here input as a voltages but not the voltage. The only difference is nothing but here I am going to take here inputs are the currents, not the voltages. So therefore this is a standard equation. So therefore here output is equal to 120. So output is equal to 120 when the IS1 is 5 ampere and IS2 is 10 ampere. So substitute here. So 5 into K1 and 10 into K2. So this is the first equation. And similarly VAB is equal to 15 volt when IS1 is 10 ampere and IS2 is 5 ampere. So therefore in place of IS1 substitute 10 and IS2 is equal to 5. So therefore 10 into K1 plus 5 into K2 it is equal to 15. This is the second equation. So therefore with these two equations we have two unknowns. So therefore if you solve K1 and K2 we are going to get minus 6 and 15. So therefore now we have to find what is value of K in such a manner when IS1 is equal to KIS2, then we are going to get VAB is equal to 0. Same thing, VAB is equal to 0, and here K1 into IS1 is nothing but K into IS2. So K into IS2. So K2 into IS2 is again same IS2 only. So therefore we know the value of K1 which is minus 6 and K2 is 15. So now I am going to take this to the LHS. So therefore 6K into IS2 is equal to 15 into IS2. So IS2 has to get cancelled. So therefore K is equal to 15 by 6 which is nothing but 2.5. See the correct solution of this question. So therefore the answer of this solution is K is equal to 2.5. So therefore when IS1 is equal to 2.5 times of IS2, then we are going to get VAB is equal to 0 for this particular conditions. So finally what I am trying to say is nothing but this is a easy way. So therefore any output voltage is equal to some constant times the input plus another constant times the another input. It is nothing but superposition. Same by using superposition also the net output voltage is equal to the output voltages with respect to only one source. Individual source we have to add. This is only for the current and the voltage but not for the power. So therefore this is a, by using the standard equation only we have solved this numerical. So now we are going to solve the sixth question. See the question here. So what is the potential drop across the 80 ohm resistor in the figure? So we have to find what is the potential drop across the 80 ohm. So what are the four options? Option A 20 volt is the correct solution of this question. So let's solve this numerical. So for this circuit diagram we need to find what is the voltage drop across this 80 ohm we need to find. So therefore this is a series circuit of resistance 80 ohm and 20 ohm and this is a source voltage. By using the voltage division principle, here the source voltage into resistance across dot we need to find the voltage by sum of the individual resistance, which is 25 into 80 by 80 plus 20. So if you solve this one we are going to get 20 volt. So by using this voltage division principle only we are going to solve this numerical. So now we are going to solve the seventh question. See the question here. So what is the current through the 5 ohm resistance in the circuit shown? So therefore here in this 5 ohm resistance we need to find what is the value of the current in this circuit. So what are the four options? Option C 2.66 ampere is the correct solution of this question. So let's solve this numerical. So for this circuit diagram we need to find what is the current in this 5 ohm we need to figure out. Only the magnitude value we need to figure out. So therefore here what I am going to do is, this is a practical current source. So I am going to convert this practical current source to a practical voltage source. So therefore the practical voltage source value will be a product of the current and the resistance, which is 5 into 4, which is nothing but 20. Here the plus has to be in the arrow side. So wherever the arrow is there you have to keep the positive, and the tail means negative. So positive, negative, and your practical voltage source will be same resistance will be there, 4 ohm calculated in the series. And similarly this practical current source also I am going to convert to the practical voltage source. So therefore the voltage value will be current into resistance value. So therefore 10 into 6 is nothing but 60 volt. Same arrow means positive, tail means negative, and also the 6 ohm will become in series with this voltage source, practical voltage source. So therefore this is the practical voltage source and practical voltage source. So let me assume this is a current direction. So no need to worry, you can take in any other manner. Finally you are going to get the correct way. So now I am going to assume this is a current direction. So therefore here by applying the KVL, so negative positive means there is a rising potential plus 10. So always current goes from higher potential to lower potential, higher potential to lower potential, higher potential to lower potential. So now I am going to travel in this direction. So therefore plus to minus means there is a drop, minus 6i. Plus to minus means again there is a drop, minus 5a. Plus to minus means again there is a drop, minus 4a. Again plus to minus means there is again drop, minus 20 is equal to 0. So if you solve this one, I is equal to 60 minus 20 by 4 plus 5 plus 6. It is nothing but 2.66 ampere. So therefore the amount of current which is going to pass through this 5 ohm resistor is nothing but 2.66 ampere. So we are going to solve the 8th question. See the question here. What are the Thevenin equivalent voltage and the Thevenin resistance between the terminals A and B of the circuit? So for this A and B of the circuit, we need to find what is the Thevenin voltage and the Thevenin resistance. So what are the 4 options? Option D, 41.61 voltage and 70 ohm is the correct solution of this question. So let's solve this numerical. This is a circuit diagram. For this circuit diagram, we need to find what is the Thevenin voltage and the Thevenin resistance across this terminals A and B. We need to find. So this is called as a Thevenin voltage. So this voltage across this resistor R3 is called as a Thevenin voltage. So therefore RTH and VTH we need to figure out. So by using the voltage division rule, so therefore here VTH is equal to source voltage into this resistance by sum of the individual resistance value. So therefore 100 into 120 by 68 plus 100 plus 120. So therefore 100 into 120 by 68 plus 100 plus 120, which is nothing but 12,000 by 288 is equal to 41.66 voltage. This much amount of voltage drop. And similarly now I want to find what is the Thevenin resistance. Thevenin resistance across these terminals. So therefore the principle is here, you need to remove all the ideal voltage source and the ideal current source. Means we have to short circuit the ideal voltage source and also open circuit the ideal current source. So therefore here there is only one ideal voltage source. So therefore now I am going to short circuit this one, and now I am going to find what is the Thevenin resistance across these terminals A and B. So therefore this R1 and R2 are connected in series, and overall it is going to parallel with the R3. So therefore here RTH is equal to R1 plus R2 parallel with R3 is equal to, so therefore R1 is nothing but we know 68 and R2 is equal to 100. So 68 plus 100 and R3 is nothing but 120. So 68 plus 100 is again 168 parallel with 120. So if you solve this one, 168 into 100 by 168 plus 120. So if you solve this one, we are going to get 70 ohm. So therefore here, finally this whole circuit will be like this. This is the Thevenin voltage and also this is the Thevenin resistance. So therefore overall this is called as the A and B. So therefore here this whole complex circuit is simplified to a very simple circuit of the some voltage source and a resistance. So therefore this is a very simple circuit. So the voltage VTH is equal to 41.66 volt and RTH is equal to 70 ohm. So now we are going to solve the 9th question. See the question here. So what is the hexadecimal representation of the 6578? So therefore we need to find what is the exact decimal representation of this octal number 657. So therefore out of the 4 options, option A 1AF is the correct solution of this question. So let's solve this numerical. So now this is an octal number. So octal number we have to convert to a hexadecimal number. So therefore the standard procedure is nothing but, now what we are going to do is we are going to convert this octal number to first binary. So therefore we are going to convert this octal number to binary, and from binary we are going to again convert to the hexadecimal. This is a very standard procedure. So what we are going to do is first we are going to convert this octal number to binary number, and then we are going to convert this binary number to the octal number. So here the first thing is we are going to convert from octal number to binary number. The standard procedure is here each and every digit in octal number must be represented by a binary number of 3 digits. So therefore for 3 digits is nothing but from 0 to here 000, 001, 010, 011, 100, 101, 110, 111. So this is called 0, 1, 2, 3, 4, 5, 6, 7. So what we are going to do is in the octal each and every digit will be represented by 3 binary numbers. So therefore here 6 is nothing but here 110. So therefore 6 is 110, and 5 is nothing but 101, and similarly 7 is nothing but 111. So 111. So what we have to do is we are going to convert this octal number to binary number. So therefore this is a binary representation. But now what we are going to do is we are going to convert from binary to hexadecimal. So binary to hexadecimal is nothing but here we have to group the 4 digits. So therefore here 4 digits means this 4 digits. So you have to do all the patterns, and then we have to do 0 to 15. So 10 is nothing but A, 11 is B, 12 is C in hexadecimal, and 13 is D, 14 is E, and 15 is F. So here we have to group the 4 digits. So therefore from the right to left we have to do the grouping from 4 digits. So therefore 1, 2, 3, 4. This is the grouping 4, and similarly 1, 2, 3, 4. So therefore this is 4. So only 1 is left. So therefore remaining 3 things we need to figure out. So therefore this is called as a zero padding. So we have to add the extra zeros. So therefore 1, 2, 3, 4. So sorry 3. So total there are 4 things. So we have to group from right to left in such a manner. So therefore this is 4, and there is only one number. So therefore you have to add extra zeros. Then this process is called as a zero padding. So therefore we have got 4 digits also. So this 1111 is nothing but 15 in the decimal, but in hexadecimal its value is F. So therefore this is F. And similarly 1010. So 1010 is nothing but 10. So in hexadecimal it is A. So therefore A. And similarly 0001. 0001 is nothing but 1. So therefore 1. So finally what we have did is we have converted the octal number to a binary number, and from binary number we have connected to the hexadecimal. So therefore this is nothing but here 1AF. So therefore this is a hexadecimal representation. This is the correct solution of this question. This is the last question of this lecture. See the question here. So what is the octal equivalent of this number? So therefore this is a decimal number. We have to convert to the octal system. We need to figure out. So what are the 4 options? Option B is the correct solution of this question. So let's solve this numerical. So in this question they have given that decimal number system. We have to convert to a octal system. We need to figure out. So the standard procedure is nothing but if you want to convert any decimal system to any other number system, the standard procedure is the numbers which are the left of this point has to be divided by that number system, and the numbers which are present at the right of this number has to be multiplied by that number system. So here there is a number octal is 8. So therefore the numbers which are present at this left of this dot is 5, 6, 2, 1. So now we have to divide. So therefore divide. So if you divide, this number is going to multiply by 702 with a remainder of 5. And similarly if you divide again with 8, so you are going to get 87 as a quotient, and the remainder is 6. And similarly again divide by 8. So therefore you are going to get 8 tens are 80, and the remainder is 7. This is called as a quotient. These numbers are quotients, and this is called as a remainder. So therefore again 8 ones are 8, and the remainder is 2. So therefore you have to take in this manner. From this manner you have to take the numbers. Only the 1, 2, 7, 6, 5. Only this remainder values you have to take. So therefore 1, 2, 5, 6, 7. So 1, 2, 5, 6, 7. In this manner you have to write. So you got this one. Now you have to figure out what is the octal value for the 125. So therefore 0.125. You have to take again 0.125 into, now you have to do the multiplication with respect to 8. If you do, you are going to get here 1. So this is the number 1. Suppose if you have got some other values here, then you have to do again multiplication. But finally you have to get only one number. One or means any number like this you have to get some k dot 000. So k can be any 2. You are getting this number. You have to do the multiplication with respect to 8. So in the initial only we have got the 1. So therefore here this is the number you have to take here. So therefore this you take here. So 1. So you can keep any zeros. No need to worry. So therefore here in the options there is only 2 zeros, means keep your zeros. So therefore this is the correct solution of this question. By this lecture we have successfully completed the 10 questions which are the previous 8 questions of the IES or ESE electrical engineering from 2017 to 2020 prelim solutions in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever I upload a new video, the direct notifications comes on mobile. If any improvements here in your villages, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care and bye bye.